Hello, everyone. Thank you for this kind invitation. I'd like to thank Godwin and Jones and all the other organizers for extending this invitation and this nice opportunity to talk about image quality in low field MRI. I have a couple of quick disclosures, um, and then we can move on to the next slide. Here is what I'm going to be talking about today. I'll tell you why it is important to look at image quality at low field, discuss some of the image quality results from a laboratory at 47 millitesla. Also look at some of the tools that we can develop at zero point 0.2 T and beyond. Some of them collaboratively with folks from Uganda and Kenya. And finally conclude about our findings. Did you know that two-thirds of the world does not have access to MRI? We reviewed this in 2019. And it's important to know the definitions for these terms from the World Health Organization. I also want to point out that in addition to accessibility being defined by WHO as trying to improve equitable access, another important term is appropriateness, meaning that you need to use the right tool for the right challenge. Here is a version of a picture that you might often see in slides, um, that the regions with the highest populations, including Africa, have some of the least scanner densities. When we analyzed these barriers, we identified two buckets of challenges. The first bucket, of course, is related to the scanner itself, which is quite expensive, requires sophisticated engineering. The sighting can get expensive too, requires a lot of power, and compared to other whole body imaging modalities is quite slow. An often less discussed topic is the lack of local resources to run and sustain these systems, such as an MR technician, a physicist, a radiologic nurse, and the radiologists themselves. An important caveat, though, is that increased accessibility does not mean suboptimal image quality. Hence, the definition of appropriateness is quite relevant here. That means one needs to identify the pathologies that can be imaged with lower SNR and in unconventional settings. On the other hand, the image metrics to achieve this appropriateness could be related to mostly image quality, so that you get consistent image quality and scanner operation in those unconventional sites or in community settings. With that in mind, let's look at our data from 47 millitesla. Our experiment included 3 sessions every day and 10 such days. We performed these experiments on the magnetic cube from Multiwave, which is the first prototype, based on Tom and Andrew's design. We looked at imaging a phantom called the Pro MRI Phantom with a 3D turbospin echo sequence and off resonance maps before and after the imaging sequence. Here's a snapshot of how the protocol looks like and the scanner on the left. Here are the imaging parameters. We did have a control acquisition at 3T with a 2D turbospin echo, and you can see the differences in time and resolution between the two at the bottom two rows. We measured a bunch of parameters. To begin with, we did look at temperature and humidity at three different locations: at the mouth of the bore in yellow, the center of the bore in orange, and the ambient temperature and humidity in green in the room. The scanner's power supply was turned off after every session, except for day one and session one when we wanted to start the experiments. And here's an overview of the different parts of our pipeline. In the reconstruction was mostly about drift correction and filtering case space. The post-processing involved off-resonance correction using conjugate phase reconstruction and using the B0 maps. Then we selected some of these slices from the 3D images to look at tests prescribed by the Pro MRI and the ACR, mostly for purposes of image uniformity, geometric distortion, and signal to noise ratio. So on the right, you can see our workflow for computing the SNR and geometric distortion and the slices that we've picked. On the temperature and humidity, on day 7, we found a dip, but that was across all locations. So it was an ambient change across the room. And you can see, other than that one observation, most of these uh, data points across days are grouped close. As we know, with increase in temperature, there was a decrease in frequency. This is well documented. But what was more interesting to us is that there is a variability in the frequency depending upon the time of day. Here's the spatial distribution of the B0 for the 47 millitesla scanner, characterized using a robot that Ivan in my lab built. And as you can see, at the point where we are going to image the human brain, it's quite homogeneous. Once you take a look at the maps, the B0 maps before and after the 3D TSC imaging acquisition, you can see from the bottom row that more often than not, there's a global shift. However, on day 10, we saw a sudden increase in one of the maps that we've not seen before or after that event. However, we don't really understand the reason for that particular event. And that did not affect the image quality when we did the subtraction as well. One important thing that we did identify looking at 3T was that the time of day when human volunteers were imaged did have a bearing on the morphometric measures. When we looked at our data, we identified that session 1 was probably the best to image volunteers because it had the least frequency shift. Here are some representative images of the Pro MRI Phantom scanned at 3T with the 2D turbo spin echo and with the 3D turbo spin echo on the 47 millitesla. We can see with correction in the rightmost column in C, the shape of the phantom is better recovered and matched, but you can also see the shift in slices because of the off resonance correction, which we did using conjugate phase reconstruction. We have our own toolbox called the Octopus, which is an open source tool for off resonance correction. Here is one slice over all 30 sessions showing you the difference between before and after correction, which you can see in the orange and red arrows pointing to the geometric distortions that have been corrected, but then you see some of the shading that happens because of the off resonance correction in yellow. Here is the quantitative results of the image quality metrics of the signal to noise ratio on the left and the standard deviation, which is used as a surrogate for image non-uniformity in a region of interest where we expected constant signal intensity. You can observe that on day 1, we do have an outlier because of the way we did the power cycling. At the bottom, you see the differences between original and correction of the off resonance artifacts. in terms of eccentricity. We use this measure because the phantom was a cylinder, and for a circle, which is in a slice, you would expect an eccentricity close to zero. Again, you see the differences on day one. The two methods here, CPR Octopus and CPR, refers to the open source toolbox that we have, CPR, and the CPR that's shipped with the system. This slide shows you the results of repeatability of the image quality over the 30 sessions for frequency, SNR, image non-uniformity, and geometric distortion. You can observe that the coefficient of variation, which identifies the variability in data, is largely less than 10% in most cases. However, in session 1, you can see that these numbers have gone significantly higher, and we attribute that to the first day where we had a different power cycling and caused the data outliers that I've shown you before. Here's the effect of electromagnetic interference at low fields, given that the body does act like an antenna and pick up different sources. You see the setup containing a power source, a signal generator, a coil, which we call the EMI transmitter coil that we hooked up to the signal generator, and we had it at a variable distance. And we also did experiments in different orientations. But when it's placed um, in right in front of the scanner axially, so you can actually the results of the EMI experiment are shown here. And as you can observe, with an increase in amplitude and a decrease in distance from the bore, you can see that the EMI significantly increases. It's also reflected in the in vivo data, especially without the use of the copper cloth, which served as a, a conductive blanket so that we would block the EMI. You can see the dip in SNR significantly. When we quantify this for different amplitudes and different distances for the phantom and for the in vivo, you see what you mostly expect. That is, with an increase in amplitude for a particular distance, uh, the EMI effect tends to be more. Similarly, when you go farther away from the scanner, the EMI effect reduces. Here's where we are with in vivo image quality. On the left hand side, you can see the three orthogonal acquisitions that we perform, with the in-plane acquisition shown in the yellow square. We then pass this through a 3D super resolution reconstruction open source toolbox called Nifty MIC. And subsequently, we have now incorporated and adapted zero shot super resolution reconstruction, meaning it has not been trained on any other data set, but the data set that we want to super resolve itself, hence zero shot, for a factor of 2. And finally, we use that data to segment hippocampus shown in yellow and the amygdala shown in cyan. When we compare this in the same volunteer at 3T, you can actually see that the volumes in CC are similar. Okay, now we'll switch gears and get to point 2T and beyond. Going back to the picture about the barriers, specifically the second barrier related to the lack of local human expertise, we were inspired by the self driven vehicles from the Society of Automobile Engineers Convention of 6 phases, where there is a transfer of responsibility from the driver to the passenger. Similarly, we came up with a 6 level automation process for ensuring that the operation mostly performed by the MR technician can be eventually performed by a paramedic who supervises the overall acquisition. This would involve stages of automating the acquisition, quality assessment, monitoring the scan while it's going on, maybe even subject setup and eventually deployment. Currently, we focused on level 2, which is partially automated image quality. To that end, we want to exploit the ability of deep learning to be able to move this local expertise on site. Here's what I mean. The present day scenario in several sites includes the acquisition of the data, and during acquisition, the MR technician does review these images, and um, if it's a pass, then it's a check. Otherwise, it's a loop of reacquiring, excuse me, or mitigating the artifacts. These then go to packs, and then oftentimes there is an on-site QA or quality assessment activity that happens, which has deep expertise in this area of MR artifacts, and it either fails the QA test or unfortunately some of the data gets discarded. Our goal is to move this expertise back on site at the site of the review. And um, here's how we, in brief, MR technicians that need expertise are scarce in low resource settings. The failure of detecting these artifacts early on will require unnecessary reappointments or data loss and increased operating time and costs. What we did in the lab was to collaborate with Godwin and look at data from 0.2T, 0.360, and 1.5T, trained a couple of models to identify wraparound and Gibbs ringing, which were the most commonly identified artifacts in the dataset at 0.2D and 0.360. Also developed models for motion, but mostly at 3T, and ask the question whether it can explainably identify hotspots where the artifacts occurred. Here is a look at our data splits. For the wraparound, we leveraged the IXI dataset for training and testing, and the low field was used mostly for validation and testing. Whereas in the case of Gibbs ringing, we use the low field for all three purposes. Our architecture was a simple 2D convolution neural network and a binary classifier of whether it had an artifact or no artifact. We wanted to develop trust in the models, and we leveraged the gradient class activation maps, or GradCam for short, to ensure that our models were being able to identify artifacts rather than simply provide higher degrees of accuracy. If you cannot identify the wraparound in the through plane image in the first, you can clearly see that with the red hotspot visualization here in the GradCam maps. Similarly, you can see that for true negatives, but we did have false positives and false negatives that I'm going to quantify for you in subsequent slides with a confusion matrix. At the bottom panel, you see our results for the in-plane wraparound, and surprisingly, we did not have any false positives and false negatives. To ensure that we were being that we didn't have blind spots in training, we did challenge it with a bunch of different inputs from 3T from two different vendors and still tried to get either a false positive or a false negative, which we could not. And as you can see, wherever the wraparound occurred, you do see these hot maps, which means our in plane wraparound model has understood the meaning of identifying wraparound artifacts in both subtle and clearly obvious cases. Extending the same idea to Gibbs ringing, you can identify in these areas of true positive that the Gibbs ringing artifact identifier can pick up places where the artifact occurs. And wherever there is a red dot, that means there is an artifact. And if you don't see those red artifacts, it's a true negative. The false positives usually happen either towards the extremities on one end top of the brain or at the bottom, and we all looked at it from the T1 sagittal slices. We then also looked at classifying motion at three levels of motion, which were basically arbitrarily um, educated as 0, 1, and 2. 0 was no motion, 1 was moderate motion, 2 was severe motion. These levels were indicated by the extent of motion that we put in the simulation with relation to the number of phase lines, that phase encoding lines that were corrupted, the degree of rotation, and also the number of motion occurrences. And as you can see, the hotspots between the no motion, moderate motion, and high motion get higher and higher in terms of the hotspots as you go from left to right. And here's our prediction and the ground truth. And as you can see, there are these instances where you have stuff outside for no motion mostly. In the cases of motion, it's trying to pick up something where the motion must have occurred. Um, to further test these motion classifiers, we did multi-level, or excuse me, multi-class motion classifiers. We did test this on a prospective data set as well, where we got subjects into a 3D scanner and asked them to either lay still, move their head modestly, or shake vigorously. And as you can see, as you go from left to right, the motion models actually show an increase in the hotspot area for different levels of motion. I did commit to showing the confusion matrices, and here you see for the through plane, in plane, and the Gibbs. For the through plane and in plane, um, specifically for the in plane, you can see that we don't have false positives and false negatives, regardless of the field strength and the vendor. But all of this data that you're seeing on this slide and the previous slides were all on T1 MPH data. Um, or T1 contrast data, I should say. For the three class motion classifier, you do see that we get good performance for the true classes for the three classes, and then the false positives and false negatives are significantly lower. We did another test beyond the confusion matrix for the three class classifier is to look at the average edge strength, which is expected to be high in images with no motion corruption. And as you have motion corruption, AES or average edge strength decreases. You can also see from our predictions that the average edge strength of class 0 is significantly higher than compared to class 2, for example. We did integrate all of this into a scanner at 3T. This was a Siemens 3T Prisma. What I'm going to show you here is how you can actually go segment by segment or a block by block on a 3D acquisition and be able to identify these artifacts. And if you have an artifact identified, you can reacquire only that part, potentially saving time and ensuring that you get artifact free images. We intend to translate this to low field, given that most low field acquisitions are also volumetric acquisitions. In this particular example, the artifact ID model identified that the first segment or the first block was artifact ridden. So while the second block was getting acquired, it analyzed the first one, and now the third one is getting analyzed and it's doing the second. So once the artifact is going to get resolved, then it's probably going to give you an all clear, and it's also going to show you the hot spots and the map that I was showing to identify where the artifacts are, so that now you can actually have an artifact free acquisition like this. So in conclusion, at the 47 millitesla, um, We found that the frequency and the B0 homogeneity to be highly repeatable. The image quality also between sessions 2 and 3 were more consistent than session 1. That was mostly due to the power cycling that we had during the session 1, or especially on day 1. The time of day characterization on eccentricity is important to consider for volumetry, and we identified that doing this on session 1 is probably the best when the scanner has not been running for a long time. And the EMI shielding is essential to ensure consistent image quality. For the studies from point 2T and beyond, um, we did introduce artifact ID that could classify and also identify hotspots of artifacts. We used these GradCam heat maps that explained and built trust into the models we designed. And all of this can be easily accessed and tried out at the URL below. I also want to point to some open source resources that we have. On the left, we've just released our games with the tabletop, which is just published in 2024. And for people looking to build open source scanners, there's also the MRI for all. And those are the QR codes if you're interested. Um, we also have the Pipal Seek library that's being developed over quite a few number of years now, thanks to Maxim Zaitsev and his group in Germany for spearheading the PulseSeek format. This is the Python version of that. And with that, I'd like to acknowledge uh, Pawan, Ivan, and Shaunak for the first study at 47 millitesla, and Shravan and Marina for the second part of the study, building the artifact ID. I have a couple of very quick shout outs. We do have the second volume of Autonomous MRI as a special issue in Frontiers in Neuroimaging. People who are interested in the use of deep learning for low field specifically are encouraged to submit. We'd like to hear from you. We also have a low field MR image quality challenge, which is live now. This is going to be um, at the same time as the 50th annual meeting of the International Conference of Signal and Speech Processing. This is going to be in Hyderabad, in India, and the challenge is live now. It deals with two tracks on denoising and super resolution reconstruction. With that, I'm happy to take any questions, and here are my coordinates. Thank you all again for your attention.